computational thinking. We chose energy efficiency predictor project, and we're group 7. So for our literature review, most of our things have to deal with the HVAC system, which are crucial for maintaining comfortable and healthy environments. But these HVAC systems are notorious for being energy intensive, often accounting for 25 to 50% of a building's total energy consumption. Inefficiencies lie in the poor insulation, outdated equipment, and lack of maintenance. Some architectural factors, like building orientation, window area, and wall materials, also play a significant role in how much energy is required for heating and cooling, which, as a result, inefficient HVAC systems can lead to higher energy bills and increased carbon footprints. On the other hand, advancements in technology and data-driven approaches have significantly improved HVAC efficiency. High-efficiency units, power insulation, and smart thermostats can greatly reduce energy usage. Additionally, leveraging data models to predict heating and cooling loads based on architectural features enables more accurate system sizing and optimized performance, ultimately leading to energy savings. And that's all from our literature review. I'm going to pass it off to Liam.
All right, so to start off, we have our kind of exploratory data analysis, and this is where we have our main database and then also how we reformatted the columns for our database as well. So start off, we added our library and then we read the CSV file. The way the CSV file works is that the columns or the different features for this project came in terms like X1, X2, and X3. So in order to better define and kind of reformat what exactly each part was, we went in here and just fully renamed the columns and then put in place as true so it fully switches over and keeps the database a lot easier to kind of read. And then you can see here from our different data set values, we've got the relative compactness, the surface area in meters squared, wall area in meters squared, roof area in meters squared, overall height in meters, the orientation, glazing area in meters squared, glazing area distribution, the heating load in kilowatt hours per meter squared, and the cooling load in kilowatt hours per meter squared. So with these data values, we get a lot of floats and integers for each of the different styles. So each value from this point on, we can use later on with our inputs and just kind of use them as a float or an integer for certain values whenever we're predicting our data sets as well. And then here we have kind of a brief description of each part, the count of how many data points we have, kind of the different averages and standard deviations throughout the data points that we collected. And some of them are pretty vast, as kind of seen above. We start at 0 for certain parts, and then it kind of goes up to 0.4 and even 5 for different sections. Now I will pass it on to Cedar, and he'll tell us about the 2 different models that we created.
Okay, so I was in charge for these models, and we were only supposed to have 3 for each of these models, but instead we had 8. And we had multiple comparisons, including the heating load versus relative compactness, heating load versus surface area per meter squared, heating load versus wall area per meter squared, heating load per roof area per meter squared, heating load versus overall height meters, heating load versus orientation, heating loads versus glazing area per meter squared, heating load versus glazing area distribution. And looking at these charts, you can see the exact heating load per each chart. So like for the relative compactness, you can see how much heating load that each relative compactness could take, the surface area, how efficient each system is. And whenever Liam goes down just a tad bit more, we can see our second set of variables, which is the cooling load versus each of these areas or each of these different variables. So like you can see for the first relative compactness, you can see which cooling load is the most efficient. Same thing for the surface area, the wall area, the roof area, overall height, orientation, glazing area, and glazing area distribution. And next, I believe I'm going to pass it on to Tyler.
Yeah, so we begin by defining our features and targets. The features labeled X, including architectural attributes of a building, such as wall area, roof area, glazing, so on. The targets are the values we want to predict, the heating load and the cooling load. Next, we split the data into training and testing sets using train test split. This is a key step in machine learning. It ensures we train the model on one part of the data and test its performance on unseen data. We create separate splits for heating and cooling targets so we can model them independently. In step 6, we create 2 random forest regressor models, one for each target. Random forest is an ensemble learning method that builds multiple decision trees and averages their predictions, which helps improve accuracy and reduce overfitting. We trained both models using the dot fit function. After training, we evaluate the models by using them to predict on the test set. We then calculate the mean absolute error, which tells us on average how far off the predictions are from actual values. Finally, in step 8, we introduce 3 new building configurations and feed them into both models to predict their heating and cooling loads. These predictions are printed out clearly, giving us useful insights into how different design features affect a building's energy genes. Next, we will have Liam.
All right, and then using a similar function from the test table data that was provided for us, we can create a actual user input database as well. So we can input our own personal values here and get a predicted heating and cooling load. So I can perform a test here as well. So just kind of adding in random numbers. This can be integers, floats, whichever. We're just kind of using all of these as a float value. And then if I insert something different other than a float or an integer, then it'll give me an invalid take here and ask me to do it again. So I'll just kind of run through this real quick and add a bunch of different values. And then we can see here, it'll give us a prediction for our heating load and also our cooling load here as well. So this project was definitely a difficult one to kind of run through and figure out all the different key features that we would need to use here, especially when predicting kind of the averages for our heating and cooling load whenever using the given table of data and then also using a user interface here for some inputs as well. Um, Cedar can go over briefly on the different parts that he worked on for List Lab.
So I went over a literature review. I looked at a bunch of different websites and articles I could find. I couldn't really realistically find much data apart from the one that we were already provided, which would have been very honestly very essential for increasing the accuracy of our prediction. But Liam, can you scroll back up to my code?
Yeah.
As you can see here, we chose scatter plot as we found it to be the most efficient one out of the bar plots, the point plots, any other one we could find. We decided that this was the best one as it shows like the exact or the exact points to where we could find the most efficient route with the heating load and the cooling load. As you can see, like for roof area, 150 seems to be the best spot as it's the most used point. And yeah, that's about it. Tyler?
Yeah, so I worked with Cedar. I had to use his code for the data models to assess the model quality and build the data interface for using the two models. And I also used the models to determine projected heating and cooling loads for the possible combinations in the table. Next, we have Liam.
Yeah, and then I just went over kind of the um, reading the whole CS file, making sure we reformatted all of the different points here, and then creating this input table for users as well. Overall, our team worked very efficiently and very evenly with kind of our different spread out points here with assessing early on kind of each part that we were going to work on. Really helped just kind of keep each other accountable when working together and create a very successful project here. Thank you for listening in on our project presentation here and have a good
Thank you
rest of your
for
all's
a
day.
great year.
Great year.